Hey everyone, grade 9 students from St. Paul American School Clark, welcome! Today we're jumping right into our next explainer. We're looking at G9 Geometry, Unit 07, Lesson 05, Surface Area of Prisms, Pyramids, Cylinders, and Cones. We're going to really unpack the architecture of these 3D shapes today and visualize the math behind them in a whole new way.
Okay, let's quickly look at our agenda. First up, our lesson objective. Then we'll break down the course surface area concepts. After that, a worked example of a right cone, followed by a massive misconception you'll want to avoid regarding height versus slant. Then, a quick formative knowledge check, and we'll wrap up with a lesson recap.
All right, Section 1. Lesson objective, targets for today.
Our main goal here is to really understand surface area concepts for 4 foundational shapes. We're talking prisms, cylinders, pyramids, and cones. Now, you're probably already pretty familiar with prisms and cylinders, right? So today, we're going to spend most of our heavy lifting on pyramids and cones. If you can master those two, you're going to be in fantastic shape for this entire unit.
Moving right along to Section 2, Surface Area Concept Explanation, Anatomy and Formulas.
So think about the anatomy of a regular pyramid. It has a polygon for a base and these triangular sides that go up and meet at a single point at the top. We call that top point the vertex, and those triangular sides are the lateral faces. In a regular pyramid, they're all identical, congruent isosceles triangles. But here's the tricky part. You've got 2 entirely different heights to worry about. The altitude, or regular height, drops straight down from the vertex to the exact dead center of the base. It goes right through the empty space inside. But the slant height? That's the measurement running right down the actual physical side of one of those triangular faces. Keeping those 2 straight is absolutely crucial.
When we talk about surface area for these shapes, we have to distinguish between 2 specific types. Lateral area, which we use a capital L for, is literally just the area of the sides, so the curved part of a cone, or those triangles on a pyramid. Total surface area, capital S, is the whole shebang. It's the lateral area plus the area of the base. Think of it like a tent. If you're just waterproofing the walls of a pyramid-shaped tent, you want the lateral area. But if you need to waterproof the walls and the floor, you need the total surface area.
So let's logically build the formulas. The lateral area of a regular pyramid is just a bunch of identical triangles. The area of one triangle is 1/2 base times height. If you add all the bases of those triangles together, you actually just get the perimeter of the entire pyramid's base, which we'll call P. And the height of those triangles? That's our slant height, represented by a cursive L. So, the lateral area formula is simply L equals 1/2 P times L. For total surface area, S, we just take that lateral area and add the base, capital B. So S equals 1/2 P times L plus B. It's literally just adding triangles to a base. Now this next concept is a real game changer. Imagine a regular pyramid sitting right next to a right circular cone. What happens if you take that pyramid and start adding more and more sides to its base? You go from an octagon to a 20-sided base to a 100-sided base. Eventually, if you add an infinite number of sides, that polygon base becomes a perfect circle and the sides completely smooth out. A right circular cone is essentially just a pyramid with an infinite number of sides.
Because of that awesome geometric truth, we don't need a totally disconnected new formula for cones. We just adapt the pyramid one. Remember L equals 1/2 P times L? Well, for a cone, the perimeter of the base is just the circumference of a circle, right? Which is 2 pi r. If you multiply 1/2 by 2 pi r, the 2's cancel out and you're left with just pi times r. So the lateral area of a cone is L equals pi rl. To get the total surface area, just add the circular base, which is pi r squared. So S equals pi rl plus pi r squared. It's beautifully consistent, isn't it?
Okay, Section 3, worked example. Right cone, step-by-step procedure.
Whenever you tackle these problems, I highly recommend a simple 3-step process. Step 1, find the lateral or curved area. Step 2, if you need the total surface area, add the area of the base. Step 3, write your answer out with the correct units and round it if needed. Let's see this in action.
Here's our scenario. We have a right cone. The radius, r, is 3, and the slant height, L, is 7. Now the question only asks for the curved surface area. That means we're only finding the lateral area. Step 1, we plug our values into the formula L equals pi rl. So pi times 3 times 7, giving us an exact answer of 21 pi. Since we don't need the base, we just skip step 2 entirely. For step 3, if we write 21 pi as a decimal rounded to one place, it's about 66.0. Boom, simple, structured, and totally correct. Moving to section 4, misconception, height versus slant, avoiding a common trap.
I literally cannot stress this enough. Altitude, which we call height, h, and slant height, L, are completely different measurements. The altitude drops vertically straight down from the top vertex to the center of the base. Think of it like a plumb line hanging in the dead middle of the shape. Slant height measures the actual physical slope on the outside. Our surface area formulas absolutely require the slant height. If you plug the internal altitude into a surface area formula, you're going to get the wrong answer every single time.
But you know, sometimes a test question is tricky. What if they only give you the internal altitude and the radius, but you desperately need that slant height for your formula? Well, visualize the lines inside a right cone. The altitude dropping down, the radius going across the base, and the slant height running down the side. What do they make? They form a perfect right triangle, hiding right there inside the cone.
And because it's a right triangle, we get to use our old friend, the Pythagorean theorem. You all know a squared plus b squared equals c squared. Well, in our cone, the legs of the triangle are the radius r and the altitude h. The hypotenuse is the slant height L, so the equation adapts perfectly to r squared plus h squared equals L squared. If you're missing the slant height, you just use the radius and altitude to calculate it first. Then, and only then, are you ready to solve for your surface area.
All right, section 5, formative knowledge check. Test your skills.
Let's put this into practice. Imagine a regular square pyramid. The side of the base is 12 centimeters, and the internal altitude is 8 centimeters. Take a mental pause here. Can you figure out the slant height L? Picture that hidden right triangle we just talked about. What would the base of that internal triangle be?
Let's walk through it step by step. The real trick here is realizing that the base of that internal right triangle is exactly half the length of the pyramid's base side. Half of 12 is 6. Now, we use the theorem. Square the base leg, 6 squared is 36. Square the height leg, 8 squared is 64. 36 plus 64 gives us 100. That equals L squared. To find just L, we take the positive square root of 100, which gives us a nice clean 10 centimeters for our slant height. From there, you'd be totally ready to conquer the surface area formula.
And finally, section 6, lesson recap, key takeaways. So let's lock in the core concepts. Surface area principles apply universally to prisms, cylinders, pyramids, and cones. Conceptually, remember that cones are basically just right pyramids with an infinite number of sides. That's exactly why their formulas mirror each other so perfectly. S equals 1/2 PL plus B for a pyramid morphs right into S equals pi r L plus pi r squared for a cone. And the golden rule for today, always double check if a problem is giving you the internal height h or the external slant height L. Use the Pythagorean theorem to find the missing piece if you need it. Before we wrap up, I want to leave you with something provocative to ponder. We spent a lot of time today seeing how a pyramid logically evolves into a cone when you give its base an infinite number of sides, right? Based on that exact same logic, how do you think a prism relates to a cylinder? What do you suppose happens to the surface area formula of a prism if its base suddenly has an infinite number of sides? Think about that structural relationship. Thanks for joining me today, Focus Learners, and I'll see you in the next Explainer.